This tutorial is on the basic comparison test, a powerful test to check for convergence of a series by comparing it to another series. That means we derive knowledge about one series by using knowledge about a different series. Let us start by stating the details of the basic comparison test. Suppose we have given two sequences an and bn such that 0 is smaller or equal than an is smaller or equal than bn. Note that we only require this property to be true for all little n greater or equal to some capital N. That means it might not be true for the first 15 elements in both sequences, or the first 100 or 1000, but it is true from some point onwards, and that's all that matters. Under those conditions, the corresponding series to the given sequences an and bn behave similar, because if the series taken over the sequence bn converges, then so does the series taken over the sequence an. On the other hand, if the series taken over an diverges to infinity, then so does the series taken over bn. That means if the two sequences an and bn satisfy this relationship, then their series behave similar. When you take a moment to think about it, it becomes quite intuitive. The sum over bn converges means that if we sum up all bn, then we get something finite. Given that in general an is small or equal to a corresponding bn, the sum over all an must be finite as well. In particular, the sum over all an converges. Likewise, if summing up all an gives us infinity, then surely summing up the even larger elements bn must also yield infinity. However, it is very important to notice that the basic comparison test does not give if and only if statements. That means, if the series over an converges, that does not mean that the same is true for the series over bn. Likewise, if the series over bn diverges to infinity, we do not know what happens with the series over an. Let us take a look at some examples. First, we consider the series taken over the sequence 1 over 2 to the power n plus 1. Then the sequence elements are non-negative. There are two possible situations in which we can apply the basic comparison test. The first one being that we find a sequence bn such that our given sequence 1 over 2 to the power n plus 1 is smaller or equal to bn, and the series taken over bn converges. In this case, we could conclude that our given series converges. On the other hand, if we were able to find a sequence an such that 0 is smaller or equal than an is smaller or equal to 1 over 2 to the power n plus 1, and the series taken over an diverges to infinity, then the basic comparison test would tell us that our given series diverges to infinity. To find out if we can apply one of these cases requires some practice, but the main idea is always to look for a sequence which behaves similar to the given sequence. In our case, 1 over 2 to the power n plus 1 behaves like 1 over 2 to the power n, and if we compare them, we have the following inequality. Overall, we get the following relationship for all n greater or equal to 1. Furthermore, the series over 1 over 2 to the power n is a geometric series, and as such is well understood. In fact, because of the term a half, we know that this series converges. Hence, we have found conditions for which the basic comparison test is applicable, and we now conclude that the series taken over 1 over 2 to the power n plus 1 converges. As another example, let us consider the series taken over the sequence 1 over 2n plus 1. It is easy to see that all terms are non-negative. Again, we try to find another sequence which we can compare to our given sequence. What are our options? Well, for large enough n, the sequence 1 over 2n plus 1 behaves similar to the sequence 1 over n. Here we get the following relationship. But the series over 1 over n is the harmonic series, and as such diverges to infinity. That means the series over the larger sequence diverges. This is one of the scenarios where the basic comparison test cannot be applied, and thus our choice of 1 over n was simply not good enough. Next, we may observe that 1 over 2n plus 1 also behaves similar to 1 over 2 times n plus 1, because the only difference is that the denominator on the left-hand side is 1 bigger than the denominator on the right-hand side. Hence, we get the following relationship. Furthermore, the series over 1 over 2 times n plus 1 equals a half times the series over 1 over n plus 1. But this series is the harmonic series, and as such it diverges to infinity. That means our given sequence is greater or equal to a sequence whose corresponding series diverges to infinity. So, by the basic comparison test we conclude that our given series also diverges to infinity.